So before going to that, we should know what is that eigenvector. Eigenvector is a one type of special vector. When it operates on a vector, it gives the same vector. So here you can see eigenvector is a one special vector. Okay. When it operates on a square matrix, it gives the same vector with some multiplication constant. Okay. So when the vectors give the same vector, okay, with some multiplication constant, then we used to say that vector is a eigenvector of that matrix. Okay, so here we will take one example and quickly see how we can represent the eigenvector, what is the property of it, okay, how it is basically maintaining the direction, and if you multiply another vector with that matrix, whether other than if you multiply a vector, any other vector which is not eigenvector, then what is basically happening. So eigenvector is a one special vector when it operate on a matrix, on a square matrix, it gives the same vector. Okay, so here we have 1 2 by 2 matrix. Why you have taken 2 by 2 matrix? It is very easy to represent in that our planar way. Okay, so where we have x and y, or you can say I and j coordinate like that. It is easy for us to represent, and it also very easy to visualize. So we have taken 1 2 by 2 matrix. And also we have learned that your eigenvector solution is a two-step process. First we'll try to identify eigenvalue and then eigenvector. So once you solve it, okay, what we'll do basically, we'll take this term in the left side and we'll make it 0. At the end will come as a 0. Since we assume eigenvector is one special vector, again that vector value should not be 0. Okay, the vector should not be 0. So this bracket term should be 0. Now if the bracket term is 0, that means it's basically one matrix. Matrix basically a matrix, and lambda, that is your multiplication constants with some identity matrix. Identity matrix means whose diagonal term will be 1 1 1. Okay, rest of the term will be 0. So basically it is a one type one. It will come as a matrix. So if you want to matrix part is 0, so we will take the determinant of it and we'll make it 0. Okay, so once it, what happened, you will get these equations, and then you will get that solution here. So lambda, first eigenvalue will be 4, second eigenvalue will be 6. Now again, if you put that value, lambda is equal to 4 into the equations, you can solve that your eigenvectors. Eigenvector value of the eigenvector will be here minus 0.7071. Yes, 0.7071. Here is 7071. Both are that same 0.7071. Okay. Now what happened if you plot it? Okay. So what I did, I took Matlab and I try to get that eigenvector and eigenvalue of it and try to plot it. Okay. So if we go in Matlab and if you type it, only this comment, okay, or if you type this one only, and if you give this command, you will get that eigenvalue and eigenvector of the matrix A. So here V is basically eigenvector and D is basically one diagonal matrix. Both will be a matrix. V will consist of eigenvector and D will consist of eigenvalue, and only you will get the diagonal terms. So diagonal term, first diagonal term corresponding to first eigenvalue, second diagonal term will be for the second eigenvalue. If you have more number of degree freedom, if you have larger size, the size of the matrix is high, in that case you will get higher eigenvalue. Okay, so here we have learned that how we can get that solution in that our Matlab. Okay, so here also you can see how basically we can get. Here what I did, I just cross it, and now here you can see this is our Matlab, where this command is very common. Here I just form the matrix and then I give a comment how to get eigenvector and eigenvalues. Okay, and thereafter I take another vector that I will discuss now. So here you just see if we run that program, we will get two eigenvectors. The first eigenvector, here you can see first eigenvector here, that is your 0.7071, it is 7071. This is negative, this is positive, both are here. But for the second eigenvector, both are positive. Okay, now here, see if you plot it, so here it is minus 0.7071 and this is plus 7071, and here you will get one straight line here. Okay, basically both are the same value, so you get a straight line, which is horizontal straight line. Here it will be inclined. Okay, now you just see what actually we are doing. Okay, so here you can see that your first eigenvector we can represent graphically in this way. So basically this is your first eigenvector and the direction of eigenvector is like this, and for the second eigenvector we have the direction like this. Okay, so basically here you can see that this 2 is the eigenvector of the matrix A. Okay, and the property I already informed, that property is that if we take a matrix and if you multiply with the eigenvector, it should come with the same vector with some multiplication constant. It's like that. Okay, now what we will do, if we consider any vector, okay, if you consider any vector other than your eigenvector, what we are getting, that we'll see. Okay, so first what we'll do, we will take any vector x, okay, any vector x other than these two value, other than these two eigenvector. Okay, and we'll see what we are getting. Again we'll try to say, again we'll try to get a vector which is your eigenvector and see we are getting the same vector or not. Okay, so here we just see what we did in the Matlab. You can see here, here I took any vector, so here I took any vector here, that is your 0.5 and 0.2, which is basically not this one. So basically this is not that your eigenvector. We took any vector, and then what I did, I basically multiply the matrix A with the vector x. Okay, and then I divided with the diagonal term, first diagonal terms. Well, okay, first diagonal term, because we have learned that ax equal to lambda x. So ax equal to lambda x. Okay, so what I did, I try to get that x vector by lambda. Okay, so it should come as a x vector. Okay, so what I did, I took x as your 0.5 and 0.2. Okay, which is not the eigenvector, that is any other vector, and I then multiply with that matrix A and then divided by that first eigenvalue. Okay, and I try to see whether I am getting the same vector or not. Okay, so here you just see. So I try to check the eigenvector. So I just do the check one. Okay, check one of eigenvector. And what I did next, I take that first eigenvector here. Here you can see the V basically storing that eigenvector. So I took the first column. So basically I took the first column and then multiplied with the matrix A and then divided by our first eigenvalues. Okay. Now what I did, I try to plot. First I try to plot that first eigenvector, means this first column. Then I try to plot second eigenvector. Okay, that color is in yellow. Then third one I plot, that is check. Okay, check means that eigenvector which I get by multiplying the matrix A. Okay, and the value of eigenvector was 0.5, 0.2. And fourth one is here. Basically, I try to get that our eigenvector by multiplying the matrix A with our first eigenvector, and then I divided with that first eigenvector. So I try to plot the fourth. Okay, now I try to plot the fourth eigenvector. Here you can see, if I try to plot it, okay, now here you can see here, listen here, you can see that your fourth one basically overlapping with each other. The first one, okay, first one and the fourth one basically overlapping with each other. Okay, first one and fourth one, here you can see first one is red and fourth one is your blue. So if I try to remove that fourth one, you can see this sign, third one. Okay, So here you can see that this was a first eigenvector, and this was a second eigenvector, and this third one we achieve by taking any vector which is not the eigenvector, and we obtain that a vector which basically is changing the direction. Okay, here you can see it is changing, neither it is following this direction nor this direction, it is changing the direction, it is the direction, it is in this way. Okay, now if we multiply the eigenvector with the matrix, okay, so if you multiply with the eigenvector, so basically if you multiply the matrix with the eigenvector, okay, and then if you divide it by that eigenvalue, then it should come out the same eigenvector that we obtain in the that your fourth plot, that we obtain in the fourth plot. Okay, here you can see this check two eigenvector. I am plotting check two eigenvector here. Okay, so here you can see that if we consider the eigenvector and if we multiply matrix, you will get the same eigenvector. Okay, so basically what we have learned, that eigenvector is that vector. If you multiply a matrix with that vector, eigenvector, it will come with the same vector. And eigenvector is that vector which basically do not change the direction when you operate on a matrix. Okay, when you operate on a matrix. Okay, now you can basically try to imagine in a funny way. Okay, funny way in the sense, for example, you want to be the eigenvector. Okay, so you want to be eigenvector and you want to go from one place to other place like this. Okay, so initially we have decided that you will try to go in this direction. Okay, and in some position you meet with your friend, and in some position you meet with your friend. Okay, now if we change the direction, if we now after meeting with a friend, okay, after meeting with a friend, if we change the direction in some other places, then you will not be the eigenvector of your friend. Okay, so if you want to be the eigenvector of a friend, then what should you do? You should always take your friend with you and go in the same direction that initially you have decided to go. Then you can see you are the eigenvector. Okay, so basically eigenvector is a vector which do not change the direction when it operate on a matrix. Okay, if it change, then we cannot say that is eigenvector. Okay, so basically what happen, eigenvector size of that eigenvector, it can be enhanced, it can also be reduced. Okay, depending on the value of lambda. Lambda is value is very low. In that case, you can say, or if it's coming as a fraction, in that case, your value will be low as the original from the original one. Okay, so basically it can expand or it can contract, but it will not change the direction. Okay, so that is basically eigenvector, and we can represent the eigenvector graphically in this way. Okay. Now, if that eigenvector operate on a matrix, it should come the same. If not coming the same, if we change the direction, then you cannot call that vector as an eigenvector of the matrix. I hope you got some idea. Thank you.